What's up, fellas? Today we're going to be going over the fundamental theorem of calculus, part 1. And I'd like to apologize in advance if I sound a little congested. It's because, well, I am congested. But basically what this theorem amounts to is taking the derivative of integrals. The formal definition says if some function f, if that is continuous on the open interval a comma b, then a new function g of x, which is equal to the integral from a to x of f of t dt, so long as x is in between a and b, then g of x is continuous on the open interval, differentiable on the closed interval, and the derivative of g with respect to x is equal to f of x. So basically what this theorem is stating is that you just take this x and you plug it in. And it's so simple, it's kind of hard. So let's move on. Alright, so let's do some example problems. The directions are asking us to find the derivative of these functions. And really, the only thing you need to do for the top one is take this x and plug it into the variable. It's Again, it's so simple, it can be hard sometimes. So that would equal x squared minus 1 to the 20th. Boom, 3 points. Alright, the next one is a little bit more tricky because the x is down here, and we need to get it up here in order to plug it in. And the way we do that is just pop a negative out front, and then we can switch the limits. So x comes up here, the 2 comes up here, and then we just still have all this stiff, and this is the exact same as that. And then so once you have this, you can just plug it in again, just like last problem. So the derivative is equal to, we just have to put the negative out front, and then you have cosine x squared plus x. Oh, what happened there? There we go. Alright, so more often than not, the problems you're going to get are not just going to have x by itself as one of the limits. It's going to have a square root of x or a 2x or something just more complicated than x. Probably more complicated than 2x as well. But what we've been doing with the other problems has been plugging in x and just leaving it as the answer. However, what we've actually been doing is doing the chain rule and plugging in x and then multiplying it by the derivative of x. However, the derivative of x in our cases in the past have just been 1 because it's just been x by itself. But here we have the square root of x, which the derivative is 1/2 x to the negative 1/2. So let's do this problem. So we're essentially plugging in this, but then multiplying by 1/2 x to the negative 1/2, which is equal to root x squared over root x squared plus 1 times 1/2 x to the negative 1/2, which then is equal to just x over x plus 1 times 1 over 2 root x, which for me, that's simplified enough. You can try to simplify it a little further, but I mean, you don't really need to. Boom! Alright, so for our next problem, we'll have to find the derivative of this g of x, which you'll notice has variables in both the upper and lower limits of integration. And the way we can attack this problem is by, you'll recall there's a rule that if you have a function with the limits of integration being from a to b, say this is our x-axis, and here's a, here's b. If there's some point c in between a and b, you can split it apart by integrating from a to c, which gives us this part, and then adding it to from c to b. And those two parts give us the exact same value per se as just integrating from a to b. It's just splitting it apart. And so that's how we're going to tackle this problem. Alright, so let's split this bad boy apart. So let's take it from tan x to 0, let's say. It doesn't really matter what constant you choose. It won't change the answer. So tan x to 0 of 1 over square root of 2 plus 2 to the 4th dt, of course, and then add that to the integral from 0 to x squared of the same thing, 2 plus 2 to the 4th dt. And then notice how this integral has the tan x on the bottom, or our x, our variable, on the bottom. So we'll just need to move that to the top by popping a negative out front there. So then it's from 0 to tan x of the same thing. And then this piece is the same because our x is up top. That's a 0. Alrighty. And then to find the derivative, we just kind of apply what we've learned. We plug in the tan x to this, and of course we're not going to forget our negative. That's a common mistake. And we'll have negative 1 over 2 plus tan x to the 4th. But then, because it's a tan x and not just an x, we have to also multiply by the derivative of tangent, which is secant squared. Secant squared x. And then we have to do this piece, plug in our x squared to the 4th, and then multiply by 2x, because that is the derivative of x squared. And then, simplified even further, we get negative secant squared x all over the square root of 2 plus tan to the 4th x plus 2x all over 2 plus x to the 8th. And there we have it.